So if you consider an object that's spinning like this, and we wanted to know, the overall kinetic energy, we'd actually have to look at every single spot, right? And there's a certain radius, there's certain tangential velocity here. This has a certain amount of mass. And if you remember, what we did was with moment of inertia is look at all of those, right? Where we look at the energy of all of those as it goes through. So, we can look at each spot. And for instance, like with the moment of inertia for one singular object, we're dealing with the mr squared, mass times the radius squared. So it's located here, and we've got that. Now, if we have two, right, we have two of them, 2 mr squared. We have 2 of those, and that's the moment of inertia. And then with a ring, it's the entire mass of the ring times r squared. And then for different objects, right, we have these. Now, it takes some advanced mathematics to be able to drive these, so you shouldn't have to memorize any of them. A disk or cylinder is 1/2 mr squared. The moment of inertia for a sphere or a rod, we've got that here. And again, you don't need to memorize those. And so the big thing, though, you do want to memorize with moment of inertia is that it depends on the mass. The more mass you have, the more moment of inertia you have. And then how is it distributed? The closer the mass, the less moment of inertia there is, right? So the further out a mass is located from a spinning object, the harder it is to get it to stop, the harder it is to get it to start rotating. The more mass that you have, the harder it is to get it to start rotating. And this is definitely critical for you to remember. Now, for energy, the kinetic energy, instead of, kinetic energy translational, which is 1/2 mv squared, we have 1/2 I omega squared. And this is the kinetic energy of an object in rotation. So this is rotational kinetic energy, and we're going to use both today. So if we have a bowling ball, let's say that its speed is 6 meters per second, its mass is 3 kilograms, we can get the energy pretty easily, 1/2 mv squared. We have the mass, we have the speed squared, 54 joules. Now, that's translational energy. That's just left to right. But it's also spinning, right? So if this was sliding across the surface, let's say this is frictionless and it was sliding across, that's the only energy it would have. But because it's also rotating, we need to know that energy as well. So if we do that, again, with moment of inertia, it's how hard it is to get an object to rotate or stop rotating. There are 2 main factors, are mass and radius, right? So the more mass that you have, the bigger the radius that you have, the harder it is to either get it moving or stop moving. So for instance, this sphere versus this sphere, obviously this has much lower moment of inertia, much less mass, even though that the radius is about the same. And so, yeah, the greater the radius, the harder it is to stop, harder to turn or stop turning. And the more mass, the harder it is to turn or stop turning. So we can get the rolling energy. Let's say that the radius is 0.16 meters. The sphere is 2/5 mr squared. And we can get the energy there. So yeah, go ahead and pause the clip. Calculate the rotational kinetic energy. And when you're ready to check, you can hit play to continue. Okay, so 1/2 I omega squared. We're going to have to get the angular speed, so V equals R omega. And the angular speed is 37.5 radians per second. Here's that right here, and we have the radius. We have the mass, and 2/5 mr squared should get 21.6 joules. So the total amount of energy of it rolling and translating is 75.6 joules. So one of the things that we did today was spun our wheel, and as we spun it, I had them look at the different parts of the wheel. So the further you are from the middle, the greater the tangential velocity. And then next what I did is I took the wheel and I pulled it across the table. So if we pull a wheel across the table and not allow it to rotate, but just just pull it across, all those different parts would have the same translational velocity. Now if you actually have a wheel that's spinning, what happens is the wheel is spinning, So as it spins, you have rotational velocity, and then you also have the translational, which is right here. And both of those combine together. Now what happens is as this rotates down at the bottom, this has a rotational velocity like this, right, going this way, and then translational is going this way. So it turns out at the bottom, when you add those two up, you end up getting 0 meters per second. That's why as something rolls across the ground, you know, it's static friction, right, because it's not slipping across the ground. So again, at the top, it's a combination of the two. You have a linear plus the rotational there, and it's 0 at the bottom. Okay, so next what I did is took one of my 1 kilogram masses and I let it roll down an incline. Now, as it rolls, it's rolling faster and faster and faster as it goes to the bottom, right? Now, if this was frictionless, it would just slide down, right? It would just slide down, and all it would have was translational kinetic energy. But if there is friction here that allows it to roll, that will, you know, allow it to go. Now, one of the common misconceptions with this is with non-conservative work. In this case here, there is friction, but the friction allows it to roll. And because it's rolling friction, non-conservative work is still 0. Because if it was slipping, let's say it was rolling and slipping, like slipping across, some of that energy would turn into friction. Where the thermal energy would take away from the overall energy. But if it's allowing it to roll, then the energy is conserved. So we're going to want to practice that. Non-conservative work is 0. We're looking at the change in translational, which is, you know, the left to right, or right to left in this picture. The rotational, which is, you know, how much faster is it rotating. And then in this case, there's gravitational energy going on. So if we set this up, we have 1/2 mr squared for a cylinder. The height is 3 meters. The final height is 0 meters. The initial speed, the initial velocity is 0. The final velocity is what we want. And we also don't know the final angular speed, and we want to know what's going on with that. So again, we set up non-conservative work is equal to change in kinetic energy translational plus change in kinetic energy rotational plus change in potential energy gravitational, and those are the ones that are applicable here. 0 for non-conservative work. Translational is 1/2 mv final squared minus 1/2 mv initial squared plus 1/2 I omega final squared minus 1/2 I omega initial squared plus mgh final minus mgh initial. Now, we know that the initial velocity is 0, so that becomes 0. We know that the initial angular speed is 0, it's not rotating, and the final height is 0. Now, one of the tricky things here is the fact that, you know, we have linear speed here, but then this is angular. Now, if you remember, v equals r omega, so what really omega is the linear divided by the radius, which we can place in here. So this now becomes I, which is 1/2 mr squared. We've got that. And then we have this, which is going to be squared. So we have v over r squared times I times 1/2. And when you put this in here, the radiuses will cancel out. And so it's independent of how big the radius is. So yeah, go ahead and finish this one and calculate the speed at the bottom. And when you're ready to check, you can hit play to continue. All right, so we should get there with our radiuses cancel out. We can cancel mass from both sides. We'll get 0 equals 1/2 v final squared plus 1/4 v final squared minus gh initial. That 1/4 comes from the 2 1/2 being multiplied. And we should get 6.26 meters per second at the bottom. And yeah, so it's moving less than it would be because some of that energy is turning into rotational energy as it spins. All right, now let's say that we have that same rolling, you know, ball, or cylinder, and then it hits a spring, and that spring compresses a certain amount, X. So when it does, we want to find out how much does it compress. So if you want to try this one, again, you're using non-conservative work, and you're dealing with different kinds of energies here, though. Although, you know, change in kinetic energy, translational change in kinetic energy, rotational are still there. The third one is change in potential energy of a spring, which you might need to look up. So yeah, go ahead and pause the clip, see how far this will compress. Again, this is the same continuation from the last one, where it's at the bottom now and it's rolling and it's going to hit this spring, and you can find that out. So go ahead and pause the clip and give this a try. When you're ready to check, you can hit play to continue. All right, so we've got the values here. The final speed will be 0. The final speeds will be 0. The initial speed is what we're carrying over here, and we want to find the final position. And the initial X position, X initial is 0 here, and then it's going to get compressed. And we can simplify here for V equals R omega to get in for angular, and then our radiuses will cancel out, and we should get 1.25 meters is how much it will compress. All right, so one of the things that we looked at also is the F equals ma of rotation, which is torque equals I alpha, I being the moment of inertia, analogous to the mass, and then alpha is the angular acceleration compared to linear acceleration. And so, yeah, we can use this for what's going on with objects that are spinning faster, spinning slower. And we're going to use this here for these barrels that spin. You know, a car hits them and these barrels spin. Let's go ahead and draw one of these. What we're going to do is approximate it as a cylinder. So 1/2 mr squared will be the moment of inertia. It's going to start from rest when the vehicle hits it. And there's a force on it. We'll say it's at a perfect 90-degree angle here. And the force is 1,612 newtons on it, and the mass of these are 35 kilograms. The radius is 0.19 meters, and we want to find out what is the acceleration of this after a period of you know, this force and you know, the different dimensions here. So we're going to use torque equals I alpha for that, and then we'll go from there. So go ahead and pause the clip and do that, and when you're ready to check, you can hit play to continue. Okay, so should get an alpha of 484.8 radians per second squared. And so as long as that force is constant on there, it's going to get spinning faster and faster. So what we want to find out is if it's in contact for 1.5 seconds, how fast is it going to be moving if it's starting from rest? So omega initial is 0. We want to find out how fast is it spinning. So go ahead and pause the clip and see if you can do that, and when you're ready to check, you can hit play to continue. All right, so we can use one of our kinematic equations, and we should get 727.2 radians per second is how fast it would be moving after that time period.